Magnetic fields, part 2. In part 1, we used the Biot-Savart law, funny looking law there, to find, and we did find the strength of the magnetic field at the center of this loop of current and at that square loop of current. But there's another way to find the strength of the magnetic field. That is Ampere's law, the closed integral BdL equals mu naught I. Our task for this video is to try to demonstrate that these two laws are the same thing. That's funny, they don't look similar. One has a pi and the other doesn't. But we'll try to show that they are the same thing, and we will fail. That's part 3, but we'll fail. What we can do, however, in this part is show that these two laws are both able to find the equation for the strength of the magnetic field near a infinitely long current carrying wire and inside a solenoid. So we're trying to show that those two laws are the same. And what we'll do is we'll use the first law to derive the first equation, then the second law to derive that equation, and then we'll do 3 and 4. So let's get started. But first, we'll need a special integral. Again, a quick and dirty derivation, again, using the product rule. And there it is. You believe me? Let's use it. For this infinitely long wire, and there's a point P, we can use that right-hand rule to show that the direction of the magnetic field, again, is out of the plane of the screen here. To find some more quantities, notice that theta is different this time. Last time we were measuring theta with respect to the vertical, this time with respect to the horizontal. Also, this time we won't integrate over theta, but over dx. That explains, though, why we have a sine theta instead of a cosine theta like we had last time. There's our sine theta, and there it is, y over the square root of x squared plus y squared. That sine theta, this is r squared. Let's get to work with our special integral. You see that? That's our chance to use the special integral, and if you believe me, then looks like we're done. There you go. It was difficult. It wasn't a quick derivation, but we have succeeded in the first of our 4 jobs. Now let's derive that same equation, the equation for the strength of the magnetic field near a long current carrying wire with Ampere's law instead. And this is what that will look like. It'll look like the strength of the magnetic field times what is integral dl. It's b times 2 pi r. Yeah, that's the closed loop around the wire, and we're done. Well, I gotta say, that's a lot shorter, but it gave us the same result, so we are half done. And if the Biot-Savart law is a little bit harder, a little bit clunkier to use sometimes, it does have its own special benefits, and we'll see that as we derive the equation for the magnetic field inside this solenoid. Along the way, we'll be able to figure out the equation for the magnetic dipole moment, the strength of the magnetic field inside a loop of current carrying wire, again, and that's thanks to these intermediate results. Notice that A is different this time. In the previous video, A was the diameter. This time A will be the radius of the circle, so that's a change there. And here's another intermediate result. So that's where we're headed. This is where we start with a loop of current carrying wire. There's a little piece of that wire, and let's use the right-hand rule to say that's the direction of the magnetic field from that little piece of wire at point P. Okay, there's some quantities. And when you consider all those other little pieces of wire, you will have a cosine function here. Again, it goes back to how we choose to measure theta, express theta, and we'll have a cosine function in our equation. There's the Biot-Savart law, and there's our cosine, and there's our r squared. And there we are, getting going. Again, integrating over the closed loop means multiplying by 2 pi r, and here is our first intermediate result. Imagine what would happen if x equals 0. You don't have to imagine, I'll show you. We'll get that same result that we got back in part 1. Fun fact. But what if x is not 0? What if x is much, much larger than a? Well, in that case, you can express a new equation, this for the magnetic dipole moment. Mu is equal to I times area. Area is pi r squared, or pi a squared in this case. The magnetic dipole moment. Because this loop of current carrying wire feels a torque when placed in a magnetic field. It has energy when placed in a magnetic field. This is, by the way, perhaps a good introduction to that notion of spin or intrinsic magnetic moment as A goes down to 0, but we're moving on to the solenoid. How do you get there? By integrating this ring over a length from negative L over 2 to positive L over 2, and that means another chance to use that special integral. Good thing it still works. And working through the details ourselves, we get to our second intermediate result. And we're done. What if L is much longer than A? Well, in that case, you get the equation we were looking for. Hooray for that. But what if A was bigger than L? Well, in that case, yeah, you get the same result that that's the third time we got that equation. Too bad I can't get it with Ampere's law, but we're confident in that result at this point. Although this is also a warning. With the solenoid equation, looks like the radius of the solenoid doesn't even matter at all, and then we find out that sometimes the radius does matter. Could we say that that equation for the magnetic field inside a solenoid is only technically true for an infinitely long solenoid? Well, how do you build one of those? More on that later. First, back to Ampere's law. Let's use Ampere's law to derive that equation, and in order to do that, we will take our solenoid and cut it in half. Current going out of the page at the bottom of the solenoid, going into the page at the top of the solenoid. And we make a rectangular path. Let's add up the B.dl for this path. Here we have, there's definitely a magnetic field here, but it's perpendicular to that path there. The dot product for perpendicular vectors is 0, so 0, 0, essentially 0 magnetic field outside the solenoid, which isn't exactly true, but it would be if it was an infinitely long solenoid. 0 plus 0 plus 0 a third time, and here we do have a magnetic field times a length, and that's equal to the enclosed current, mu naught n times I. That's the enclosed current, n x's times the current for each x, and we are done. Done playing around. All right, I can't build an infinitely long solenoid, but I can wrap it around itself. I can make a toroid, and I can cut open that toroid to see current coming into the plane and current going out of the plane. Let's draw an Amperian loop. No current inside this loop. Proof that the magnetic field outside the toroid is 0. There is a magnetic field inside the toroid, of course, and the length there is 2 pi r. This is a different r. A different r. Earlier, r was kind of like the radius inside the toroid. This is the radius outside. In a way, it's different, but it is the same sort of equation that we would expect for our solenoid, which is good. And if you squint your eyes, you'll even see that equation coming back again. Not outside the toroid, however. Outside the toroid, you've got dots for the current going out of the plane and x's for the current going into the plane, and they cancel out, so no magnetic field outside the toroid at all. And we're done. And I'm okay with the fact that I did not come up with a rigorous proof that these two equations are exactly the same, because look at them. They're not exactly the same. One's better for some cases, the other is easier to use in other cases. But if you're looking for a more rigorous proof, you'll find it in video 3, and then another proof in part 4.